Tier 5 embeds crane scheduling inside a full terminal digital twin. It links crane operations to vessel berthing, trucks, rail, and storage dynamics. The twin supports what-if analysis and predictive optimization. Operationally, this helps you anticipate bottlenecks instead of reacting after queues form. This slide shows the digital twin as a system of systems model for terminal operations. Operationally, it emphasizes integration. Crane schedules cannot be optimized in isolation if berth availability, truck congestion, and rail cutoffs are coupled to the same workload. Time is 800 hours. 3 vessels are queued for berth allocation. 127 truck appointments occur between 800 and 1,000 hours. Crane C14 is scheduled for maintenance at 9:30, and the weather forecast includes a 15% rain probability at 9:45. Operationally, this is a realistic mix of demand and disruption. Baseline scheduling produces a 23-minute average delay. Proactive rescheduling, moving maintenance to 10:30, reduces delays to 11 minutes. A weather contingency limits delays to 15 minutes, and demand smoothing via truck appointment redistribution reaches an 8-minute average delay. Operationally, the point is that integrated planning can prevent avoidable peaks. The quantified benefits include 34% reduction in average container dwell time, 28% improvement in berth productivity, and 19% decrease in truck waiting times. Emergency rescheduling events drop by 42%. Operationally, fewer emergencies means more stable operations and less risk of cascading failures. Tier 6 decentralizes scheduling across crane agents. Agents negotiate assignments using consensus and auction mechanisms. The goal is emergent optimization without a single centralized controller. Operationally, this improves resilience when conditions change, and a centralized plan would need frequent full recomputation. This slide highlights distributed intelligence and the negotiation framework. Operationally, negotiation reduces coordination overhead while still ensuring agents do not work at cross purposes. The framework is what aligns local decisions with system-wide performance. 5 autonomous crane agents manage 187 container operations in 4 hours. Agent C1 specializes in urgent jobs with 96% success, while Agent C3 specializes in bulk operations with a 38% efficiency gain. Agent C4 has a 2.3-minute average emergency response time. Operationally, specialization is a sign of emergent organization. Agents learn roles that improve overall flow. Reported outcomes include 27% improvement over centralized scheduling and 89% reduction in coordination overhead. Continuous learning yields 3 to 5% monthly efficiency improvements, and the system self-heals under equipment failures. Operationally, this is resilience you cannot get from a static schedule. Tier 7 combines human expertise with artificial intelligence recommendations. Explainable interfaces help operators understand and override decisions. The goal is augmented intelligence rather than full automation. Operationally, that keeps accountability and domain knowledge in the loop, especially during rare disruptions. This slide presents the Centaur model architecture for augmented crane scheduling. Operationally, the architecture is about division of labor. The system computes and explains options quickly, while humans apply context, safety judgment, and strategic priorities. A typhoon warning triggers rescheduling under safety uncertainty. The artificial intelligence processes 847 constraint combinations in 3.2 seconds and identifies 23 feasible alternatives. Humans add contextual knowledge such as crew experience and unusual behaviors. Operationally, this is a case where data-driven optimization needs human judgment to remain robust. The explainable recommendation is to prioritize Block 7 before 1400 hours. It cites a 73% probability of high winds after 1430 and a job queue of 17 high-priority containers with 1600 deadlines. Confidence is 0.87. The reported performance score is 97.2% versus 89.4 for artificial intelligence only and 82.1 for human only. Operationally, collaboration outperforms either side alone. Measured benefits include 23% reduction in weather-related delays, 91% operator satisfaction with explanations, and 34% decrease in emergency rescheduling events. There are zero safety incidents during severe weather, and gains compound with a 4.1% monthly improvement rate. Operationally, that compounding effect is what makes sustained improvement valuable. Tier 9 maps crane scheduling into quadratic unconstrained binary optimization. Binary variables represent job assignment and time slot decisions, and constraints and objectives are encoded as penalties inside a queue matrix. Operationally, this is a different computational approach to the same scheduling goal. Find feasible, high-quality schedules faster as the problem grows. This slide introduces the quadratic unconstrained binary optimization form. Operationally, it is the blueprint for how assignment rules, timing rules, and optimization objectives are translated into a single penalty-based objective that a quantum annealer can search. This slide compares quantum and classical optimization approaches. Operationally, the comparison is about scale and time to decision. If classical optimization becomes too slow at larger instances, alternative solvers may produce better schedules within operational time limits. This instance uses 50 operations across 8 cranes with precedence constraints. It defines 2,400 binary variables based on 50 jobs, 8 cranes, and 6 time slots. It includes 847 quadratic penalty terms. The matrix is 2,400 by 2,400 with 156,000 non-zero elements, and annealing time is 100 microseconds per sample. A classical solver reaches a 2% optimality gap in 47 minutes. A quantum annealer reaches the verified global optimum in 2.3 seconds. Solution quality improves 23% over the best classical heuristic, with a reported speedup of 1,226 times. Operationally, that is a difference between too late and usable in the shift. Specific improvements include make span reduction of 34 minutes or 18%, and a 41% reduction in crane idle time. Constraint violations drop to 0 versus 3 in the classical solution, and energy consumption decreases 15%. Operationally, 0 violations is a must-have before any schedule can be trusted. This deployment example processes over 200 daily scheduling decisions. Reported berth productivity improves 28%. Reported annual savings are $2.3 million with system reliability of 99.7% uptime over 6 months. Operationally, this highlights that decision quality must be paired with reliability. This practice question asks you to formulate a vehicle routing style model for 4 cranes and 12 jobs, with given processing times, travel times, and starting positions. The objective is to minimize make span while ensuring no crane crossing violations. If you can write this model cleanly, you understand the Tier 1 foundation. For Tier 2, implement cheapest insertion, show insertion costs, and produce final schedules. Then compare against a first-fit baseline. For Tier 3, design a grasshopper optimizer for 15 jobs and 5 cranes with a fitness mix. Make span 40%, delays 35%, and travel 25%. For Tier 4, design a neural architecture search space and reward function, train on 1,000 historical decisions, and report the discovered architecture. For Tier 5, design a digital twin where scheduling interacts with berthing, trucks, and rail, and show how schedules change when you add delay forecasts. For Tier 6, define agent utilities and an auction mechanism that achieves Nash equilibrium, and quantify improvement over centralized scheduling. For Tier 7, design a Centaur interface with explainability and override controls, and demonstrate response to an unexpected equipment failure. Formulate a small quadratic unconstrained binary optimization for 8 jobs, 3 cranes, and 5 time slots. Then construct the Q matrix encoding assignment constraints and make span objectives. Estimate annealing parameters for a D-Wave style run. The point is to practice encoding real-world scheduling rules into an optimization form. Yard crane scheduling is a core throughput lever for container terminals. A complete Tier 1 model clarifies feasibility, timing, and safety constraints. Heuristics provide fast decisions. Meta-heuristics improve quality. Learning systems predict good actions. Digital twins coordinate across the terminal. Human and artificial intelligence collaboration improves resilience, and quantum approaches explore provable optimality at scale.